speaker is Clemens Vonrhein. Clemens originally come from a background in biochemistry before moving over to method and software development. He has worked for global phasing for over 2 decades, during which time he has been a regular tutor at many CCP4 workshops. His expertise covers the whole macromolecular crystallography pipeline, from data processing with Autoproc and phasing with Sharp to refinement with Buster. He's particularly keen on protein ligand complexes, and now he will tell us how to generate and use restraints in the context of global phasing. So please.
Dictionaries using grade and grade 2, anti-bumping or non-bonded contact restraints, local structure similarity restraints, the handling of hydrogens during X-ray refinement, and some generic utility restraints. Hopefully, all those different topics will make sense and 2 common themes will become clearer. That of balancing different restraint types and how restraints and validation are often interconnected. Probably the most common topic a user will deal with when it comes to restraints and macromolecular refinement is through the so-called restraint dictionaries for small molecule compounds, for example, as part of some large-scale ligand screening campaign. This requires the generation of such dictionaries from a basic molecular description, often a SMILE strength. Our dictionary generator grade was developed mainly by Oliver Smart and released in 2011. It makes use of the small molecule database from the Cambridge Crystallographic Data Center by using Mogul as a query tool. Other commonly used restraint generators like ASTRA from CCP4 or ELBO from the Phoenix group use similar approaches but might base their restraint dictionary on other databases like the COD. Crate allows the generation of high-quality restraints that are compatible with experimental, high-resolution small molecule structures, even for users without access to a local CST installation. This can be done via the Crate web server that has seen about 18,000 queries so far. Over the last few years, some limitations made it clear that a complete rewrite of that restraint generator was necessary, applying all the lessons learned from the original development. To that end, Oliver Smart started the development of Crate 2 a couple of years ago and was released in July of last year. It is based around RDKit and the CSD Python API for querying the CSD. At the same time, it provides additional tools to improve the handling of protonation states and especially ring systems and planarity restraints. Crate 2 is under very active development and part of the normal Buster release. Apart from those restraint dictionaries for new compounds or ligands, there are other restraints that work when it comes to MX refinement. One of those restraints are contact restraints, also called van der Waals repulsion, non-bonded restraints, or non-bonded contacts. Here we are going to look only at one special type of those contacts, namely those related by 3 bonds or 1 torsion angle, which are usually called 1,4 contacts. Those contacts only become active if they are shorter than the target value, symbolized here by the gray shaded area. What makes those 1,4 contacts special is that we can't just use a simple sum of van der Waals radii to define a target distance. Those atoms are often allowed to become much closer than that. The usual way of handling this is by reducing the radii of the 2 atoms by some element-specific value. The table on the right shows values typically used, and the picture on the left shows the resulting restraint for a generic 1,4 carbon-carbon contact. As you will notice, all such 1,4 contact restraints use an identical sigma value of 0.2. But is that element-specific adjustment enough? Can we really ignore those central 2 atoms and their chemistry? To check if some more fine-grained distinction between different types of 1,4 contacts is required, we analyzed over 30,000 PDB structures of good quality. For every atom, we calculated all 1,4 contact distances to find the smallest of those distances. Each contact was classified according to the CCP4 atom type of all 4 atoms involved. Looking again at carbon-carbon 1,4 contacts, we can start distinguishing them through the atom type-based classification. Each contact class had at least 100,000 observations, some of them even in the several million range. As you can see on the left, most of these distributions can be fitted fairly well by a simple Gaussian function. They also show quite distinct mean and sigma values. For example, the carbon-carbon shown for valine and threonine from the main chain carbonyl C to the C-gamma atom has a mean of 2.93 angstrom and a sigma of 0.073. On the other hand, the carbon-carbon contact within the methionine side chain has a mean of 3.22 and a sigma of 0.125. These are differences that the previous approach to 1,4 contact distances didn't take into account. The target value of 3,1, shown in gray here, defined by that previous method, only covers a whole range of actually observed minimum contact distances because that large sigma value is used. While this might seem like a useful compromise, such a very wide distribution probably only avoids the most severe clashes of poorly built initial models. It doesn't really provide any restraint for the methionine carbon-carbon side chain contact. At the same time, it not only becomes active much too early for the other contact examples shown on the left, But it also forms a much longer tail for potential outliers, as shown by the shaded 2 sigma regions to the left. We will discuss the impact these contact restraints models have later in the talk. Another type of restraint is relevant when we are dealing with multiple identical molecules within the arsenic unit. Here we might want to describe a local conformation in a general way and relate the different instances of this conformation to each other. Buster uses so-called local structure similarity restraints, which describes the environment of each atom through the distances of all surrounding atoms. The differences between those distances observed in different copies of the molecule are then restrained via a function that plateaus for large values. This has the effect that existing large differences are allowed to stay that way, since there is no longer a gradient contribution and therefore no force to make those different copies identical when they are really supposed to stay different. This type of restraint can be used not only for non-crystallographic symmetry restraints, but also to tie the model currently defined to another known structure. This so-called LSSR targeting could be useful when dealing with lower resolution ligand complex structures, where a high-quality APO model might be available, or when handling multiple crystal forms or other situations where referencing another model could be beneficial. In all of those cases, the current form of LSSR assumes that any genuine differences are either supported by very strong experimental density or have already been modeled by the user, and the task is to maintain those known differences while keeping everything else as similar as possible. However, how can we let those real differences, supported by the experimental evidence, show up in our model already at the early stages of initial refinement, without much need for manual checking and modeling? So far, we looked at differences between distances independently of where they occurred within that 5.5 angstrom sphere. As an example, we show two tyrosine side chain conformations in two chains with distances from the carbon and oxygen atom. The two distances to the C-gamma atom are fairly short and similar, 3.4 and 3.3 angstrom. Other distances to one of the C-delta atoms or to the C-theta atom are not only longer but also more different, 0.7 and 0.3 angstrom. The distance to the C-theta atom creates the largest gradient contribution and will try to force the two conformations to be much more similar. On the other hand, the closer distance to the CD2 atom has hardly any impact because the difference between the two conformations for that particular atom are much larger, 0.7 angstrom. Is there maybe a slightly better way of handling this? We are currently testing a downweighting of the functional forms of those LSSR restraints depending on the distance values themselves. This means that differences based on atoms further away from the central atom will have a slightly lesser or lower impact on the LSSR function value and gradient. The result is a two-dimensional functional form where the original LSSR V1 function is shown at the y equals 0 level in those 2D pictures. How does this change our LSSR restraints, for example for NCS restraints? You can see an effect using a simple test, 7A2L. After initial molecular placement, all chains will be identical, which does not correspond to the correct final model, represented here on the left via the very clear electron density map after refinement. The new, slightly modified implementation of LSSR allows that electron density to have a sensible impact on the refinement result, while the original implementation leaves that tyrosine of chain 2 stuck in its original conformation. When such differences have already been modeled, our current LSSR implementation will deploy so-called automatic pruning to remove truly different residues from the list of LSSR distances. However, when those differences do not already exist, for example after initial molecular placement, the proposed downweighting scheme seems to be a step into the right direction. There will be several talks throughout this meeting dealing with hydrogen-related topics in refinement. Without going into the detail and the pros and cons of different approaches, let us just describe what tools Buster provides when it comes to hydrogen handling in X-ray refinement. Roughly speaking, there are two possibilities. We can place a hydrogen at a nuclear position or at a shorter electron cloud position. This choice has to be made not only at the initial hydrogenation step, but also for restraint definition within refinement and during any model validation step. And of course, that decision has consequences. When placing the hydrogen at the electron cloud position, we can use full occupancy and have those hydrogens visible to the X-ray part of refinement, for example, when computing structure factors. On the other hand, when placing hydrogens at the nuclear position, we should probably use an occupancy of 0 when refining against X-ray data. Then those hydrogens will be invisible to the structure factor computation. In both cases, hydrogens will be visible to the geometry part of refinement, obviously with different bond restraints and also adapted contact term restraints. Please note that Buster does not use a so-called riding hydrogen model, but instead treats those atoms in the same way as any other atom, but with usually much tighter restraints. Although we only really have two possibilities here, it still makes all subsequent steps potentially more complicated and prone to user errors. So is there a third option? What Buster provides is a mixed mode or hybrid model. Here the nuclear position is used for everything related to the geometry part, while the electron cloud position is used whenever X-ray structure factors are computed. For the X-ray part of refinement, the electron cloud position is the only option anyway, but for the geometry part, one could use either. We've decided to use a nuclear position for the geometry part in this hybrid model to be in sync with all other non-X-ray methods like neutron crystallography, NMR, QM calculations, etc. This is most likely not the final word on hydrogen positions during MX refinement, but it might provide an additional tool to bridge the gap between the models out of X-ray crystallography and users of those models that might come from very different fields. Whenever you use an explicit hydrogen model with BASTA, the output model will contain those hydrogens and subsequent validation needs to be made aware of that fact. It also needs to be told which hydrogen position was being used when generating that model. Not all the restraints one might want to deploy during refinement will be generated automatically by BASTA. Some need specialist knowledge and methods or explicit user interaction. For that, the jelly component of BASTA supports the definition of generic distance, angle, and torsion restraints, as well as a restraint to handle partial occupancies, for example, when dealing with alternate conformations. Those restraints can be generated by various external tools and systems, some of which are provided via web services or are part of CCP4, like ProSmart and libg. Although not all of them support the direct generation of BASTA-compatible jelly syntax, the conversion is often trivial. One example of such additional restraints could be metal coordination, like hexacoordinated magnesium ions in different environments. Having given a short overview about different types of restraints within the BASTA system, let's take a step back and ask a few questions about these restraint types. Do they work well together? Are we using the right types, and do we have enough or too many? And finally, what about validation? Let's look at an example where refinement doesn't seem to go according to plan, at least when looking at the sidechain rotamer analysis performed by Molprobity. This kind of validation is often used to judge model quality, and outliers are considered problematic and highly unlikely. When taking, for example, the deposited 6DOE model and running BASTA refinement on it, we go from 1.8% rotamer outliers to nearly 7%. This seems problematic, but looking closer, we see that a lot of those newly introduced outliers come from the allowed region of each rotamer, not from the favored region. Those are then pushed into the neighboring outlier category by BASTA refinement. So what is happening here? Let's look at leucine B23. On the top left, you see the deposited sidechain conformation in the allowed region of the empty rotamer. The electron density map after BASTA refinement might already give an indication what should be done here. The deposited model doesn't quite fit the density very well. On the other hand, the refined BASTA model fits the density relatively well, at least for one of the C delta atoms. The other one is sticking out of the density near the top. When using Kuhn's auto-fit rotamer functionality, we get a rather nice fit of the TP rotamer to the BASTA density. And for comparison, we also show here the TP rotamer based on the deposited coordinates, meaning without any main chain adjustment, and the map and model from PDB redo, which also shows some indications of an alternative rotamer via the electron density map. The second example is leucine A10. Here the deposited MP rotamer is rather rare with 2.4%, and the sidechain is only in the allowed region of that rotamer. After refinement with BASTA, the density becomes a little bit clearer towards the rotamer, and one should probably use here something else. And the BASTA model itself seems to fit the density rather well. However, this is still marked as an outlier because that conformation was obtained not through a 180-degree rotation of the sidechain, but rather through an inversion of the pseudo-chiral center on the C-gamma atom. The two atoms CD1 and CD2 are chemically equivalent, but with different atom names, so sidechain torsion angles will come out with different values. By swapping the atom names, we achieve a favored conformation for the much more likely MT rotamer, in the same way PDB redo did it in this case. What does this example tell us here? That rotamer validation is very useful, especially during refinement and modeling. It can highlight potentially problematic sidechain conformations that then require looking at the actual electron density. Ideally, an outlier should not trigger the application of explicit rotamer restraints during refinement, at least not when there are better indications in the electron density maps themselves. We've talked about the 2019 change in BASTA regarding 1,4 contact terms. So what effect does a change of the contact term implementation has on refinement and overall model quality? We took some 4,000 X-ray structures from 2021 with report resolution of 2 angstrom or better and compared the geometry-only refinement or idealization using the two different implementations. We also checked the effect of using or not using torsion restraints, since those contact terms are clearly related to torsion angle restraints. Looking at a simple sidechain like leucine and its currently defined set of 8 rotamers, we see 2 very dominant rotamers, MT and TP, and 6 other much less populated ones. Taking a small subset of single residue examples for each of those rotamers, we then run geometry-only refinement using the 2 different ways of handling those 1,4 contacts. Each test was run once without and once with torsion restraints being active. we would expect those favored rotamer conformations to be maintained, assuming that the rotamer analysis and the geometric restraints are correct. What we see, however, is that without explicit torsion angle restraints, the old 1,4 contact term handling pushes nearly all rotamers into the outlier category, apart from MM. Only by adding explicit torsion angle restraints can we force some back into the allowed or favored category. With the new version of a full atom type based 1,4 contact term, on the other hand, we see that even without an explicit torsion angle restraint, most rotamers maintain their favored conformation, apart from some very low frequency rotamers. Adding torsion angle restraints improves that picture a bit, apart from the TM rotamer. Of course, this might just mean that those new contact restraints don't actually do very much, and it was the old contact terms that did all the damage. After all, we already start from defined and favored rotamer conformations in that test. So let's look at what happens when we use a set of 74 rotamers that are defined as outliers in the deposited structures. Can our restraints move those into more favorable conformations all by themselves, without using explicit rotamer restraints? We see very little impact from those original 1,4 contact term definition here. Nearly all examples stay in the outlier category. Even when adding explicit torsion angle restraints, we achieve only a rather mixed picture. The new atom type based 1,4 contact restraints already improve a significant number of those poor side chain conformations. And when adding explicit torsion angle restraints, we end up with 3/4 of the side chains now in the favored category. This suggests that those torsion angle and contact restraints are better balanced and together describe sidechain rotamers reasonably well. The impact of a change in 1,4 contact terms on sidechain rotamers seems quite obvious. After all, these are contacts of atoms that are connected through a sidechain chi-angle, but there are other effects visible as well. Here we look at the RMS bond and RMS angle values that are achievable with the same set of refinements as shown before. We would probably expect little impact on those metrics, but what we see isn't quite as simple. With the old van der Waals-based 1,4 contact term, we get rather large deviations from ideal bond and angle values for those bottom rotamers. This shows that this type of contact term is not really compatible with those rotamers. When adding the torsion restraint, we do even worse here, and this happens for the two most probable rotamers too. With a new atom type based 1,4 contact, we achieve quite low deviations from ideal bond and angle values in the refinements without torsion restraints. Even when switching on torsion restraints, the values are much lower than those for the old van der Waals based restraints. The RMS angle values are still maybe a bit high, showing the need for further investigation. So where do we stand? The quest for improved restraints is not yet over and probably never will be. From time to time, we need to revisit existing restraint types and maybe look at new ways to encode prior information. Because all restraints ultimately act upon the same underlying atomic model, the different types of restraints will most likely influence each other. So whenever we change or add a certain type of restraint, we need to be certain that we are using the correct restraint, providing the right amount of prior information and find the right balance between those geometric restraints. We need to take special care when our restraints are closely related to a validation criterion. There's always a tendency of taking a validation metric as a target for refinement, with the result that it becomes useless as a check of model quality. That is why we usually don't use Ramachandran restraints during refinement. We should probably also place rotamer restraints into the same category, because invalidating a validation metric robs us of a very powerful tool for sanity checking. I would like to thank all the people that contribute to this work, either as developers or users that provide us with reports and contributed to discussions. I would like to especially thank Oliver Smart, who started a lot of the developments described here and is the main author of our new grade 2 restraint generator, and everyone else working in our global phasing or who at some point was part of that group led by Gerard Begonia. Nothing would have been possible without the support from the members of the Global Phasing Consortium, including the distribution of all our software free to academic users. And of course, the possibility to use some fabulous external software and work with those developers has been a real joy, something very much in the spirit of a framework like CCP4. So now I'm happy to take any questions if there's some time left.
Thank you very much, Clemens. Very interesting talk. So from the Slack channel, there are no questions yet. And also in the Q&A, Rob, you have any question?
Okay, yeah. So while we're waiting for questions to come in, so very general question, Clemens. What do you think is missing from the community? What would be really useful in terms of tools? What's difficult that we haven't done yet?
Well,
in terms of ligands.
In terms of ligands.
Ligands and what have you.
I think what a lot of times is missing is, and I think Andrea mentioned it in her talks, is that quite often we're never quite sure the model that we are looking at or harvesting from the PDB, how good really does it represent the data? So anything where the deposition of the original data or the unmerged data, or even better, the raw images can be attached to it, it will at least allow us closer connection between the model that we're trying to analyze, make sense of, or restraints to harvest from it, to go actually and check what the data is telling us.
So coming back to hypothesis testing.
Yeah.
Sounds good. We got any other questions? I know we are running late already, so I'm sure that they will come in, but shall we pause at this point, answer any questions that come up in the Slack group, and we will move on and